I am Dr. Kusum, and I am teaching the course of Electrical Machines 2. In the course of Electrical Machines 2, the content is 3-phase induction motor, then single-phase induction motor and synchronous machines, which includes the synchronous generator as well as synchronous motor. So basically I am in a between, and I am teaching the 3-phase induction motor, and in 3-phase induction motor today's topic of discussion is losses and efficiency of 3-phase induction motor. The losses are very important part of the electrical machines, and we always tries to minimize these losses that are occurring in any kind of electrical machines so that we can have the maximum efficiency. Maximum efficiency is basically a conversion efficiency, which basically indicates how much power has been converted into the useful output in comparison of the input. So in the motor, the input is electrical and the output is mechanical. So here the efficiency indicates how much power mechanical has been converted out of the input electrical power in the machine. So just trying to know where these losses are occurring, and then we can say, or we can find out how these losses can be minimized and how the efficiency can be calculated. So just for knowing all about that, we first would like to know or like to see the power flow diagram of 3-phase induction motor, which basically indicates how power flows in 3-phase induction motor. So we are just trying to see the power flow in the 3-phase induction motor. So this is the power flow diagram, which has already been drawn so that the time of the video can be minimized. This is the power input P in, and this P in is equal to 3V1 I1 cos phi. Here V1 is the per phase voltage applied across the stator winding, I1 is the per phase current flowing in the stator winding, and cos phi is the power factor or input power factor of the induction motor. 3 is because we are just talking about 3-phase induction motor, 3 has been taken here. So input power is electrical. Then when the voltage is applied across the stator winding, the current flows, and as the current flows through the stator winding, the resistance of the stator winding opposes the flow of current, and due to this resistance the stator copper loss occurs. So first loss that we come across in 3-phase induction motor is stator copper loss, and this stator copper loss is numerically equal to 3I1 square R1. Here I1 is, again I said the per phase current flowing through the stator winding, and R1 is the per phase resistance of the stator winding. So this is the stator copper loss which occurs firstly in the induction motor. Then when the current flows in the stator winding, the magnetic flux establishes, and due to this magnetic flux, the stator core losses, which includes the hysteresis and eddy current of 3-phase induction motor, these losses happens. So the second loss that exhibit in 3-phase induction motor is stator core losses. These stator core losses are depending upon the frequency of the applied voltage, the voltage itself, and the machine parameters, that is the magnetic circuit of the machine. Then the power, which is because stator is a static assembly, no mechanical losses can take place. So now the power which is left at the stator, that is after feeding the stator copper losses and stator core losses, the power which is left, it is the power called as PG. This power PG is called as air gap power. Since the 3-phase induction motor is a singly excited motor, the power transfers through air gap to the rotor. From stator to rotor, the power is transferring via air gap, and that is why the power is known as air gap power. This PG is, or we can say this PG is the output of stator, or it is input to the rotor, or it is the power which is available in the air gap. So all three are same. We need not to confuse the power which is output of the stator, the power which is input at the rotor, and the power which is there in the air gap. All three are same. And this is known as air gap power, and this power is very important. So then the power which is arrived at the input of rotor, it induces the voltage at the rotor winding, and due to that the current flows in the rotor winding, because rotor is already a short circuited assembly. So when the rotor current flows, the rotor current is I2, and when the rotor current flows through the winding, the rotor copper losses happens, and these rotor copper losses are numerically is equal to 3I2 square R2, where I2 is the current flowing through the rotor winding, again per phase current, and R2 is the per phase resistance of the rotor winding. Now the power which is travelling in the air gap is numerically equal to 3I2 square R2 divided by S, and S is the slip of three-phase induction motor. Now after fulfilling these rotor copper losses, which are nothing but the 3I2 square R2, the power which is left at the rotor, it is mechanical power. We have not taken the consideration of rotor core losses, and the reason is rotor frequency is, or the frequency, electrical frequency at the rotor side is very small, that is equal to Fr, and Fr is nothing but the S into F, and it is very less in comparison of the supply frequency F, and that is why the concern or the consideration of rotor core losses is not being taken care while calculating the efficiency of the induction motor. So we are only taking care of the rotor copper losses, and the remaining power it is converted into mechanical. So mechanical power is basically the power Pg minus these 3I2 square R2. So it is Pg minus 3I2 square R2. I am substituting the value of Pg, then the mechanical power becomes 3I2 square R2 into 1 minus S upon S, and S is the slip of three-phase induction motor. Now mechanically this power will be equal to the torque into the angular speed of the rotor. From this we can just calculate the expression for the torque, that is torque which is developed, electromagnetic torque at the rotor, and the electromagnetic torque becomes equal to this power divided by the rotational speed of the rotor. Here when we convert this rotational speed of the rotor into the synchronous speed, the term 1 minus S cancels from the numerator, and the ultimate expression which is left is 3I2 square R2 divided by S divided by omega S, and it is Pg by omega S. Pg is the air gap power, and omega S is the angular synchronous speed of the stator of the motor. This torque here, by substituting the elaborated value of I2 in terms of the circuit parameters, we can just find out a detailed expression of the torque developed. For a motor, torque is an important parameter of the concern. Here, after power is converted into the mechanical, then the mechanical losses, which are friction and windage losses, these losses happens, and the power which is left after fulfilling these mechanical losses is ultimately appearing at the shaft, called as useful power, shaft power, or the output power, or all are same. So it is shaft power, output power, or the useful mechanical power. So if we calculate the overall efficiency, or before that we can just see how much shaft torque will be available. So for that the shaft power is calculated, and the shaft power is P mechanical minus the mechanical losses, and this power will be again equal to the shaft torque into the rotational speed, that is omega R. So shaft torque can be found as P shaft divided by omega R, and it is the useful shaft torque available at the machines or the motor's shaft. Now the efficiency of the motor can be found as the shaft power PSH divided by P input. Now the shaft power is the ultimate output of the motor, and input power that we have already stated, it is 3V1 I1 cos phi. Apart from the efficiency of the motor, there is one more efficiency can be defined, that is called as Rotors efficiency. So in the Rotors efficiency, the output is shaft power, that is output of the rotor, and the input is input to the rotor, which is nothing but the PG, that is air gap power. So this PG is the input of the rotor, and the neta rotor is defined as P shaft divided by PG, whereas neta motor is defined as P shaft divided by P input. So this is how the power flowing into the three-phase induction motor, how the losses are occurring, and how the power is converted from electrical to mechanical, and then the concerned expressions by which we will be able to calculate the efficiency of the motor, different type of losses of the motor, efficiency of the rotor, shaft power, shaft torque, electromagnetic torque developed, and the total electrical power, mechanical power developed inside the motor. There are a lot of numericals which are very frequently asked on this particular topic, and that requires the complete knowledge of these expressions. These expressions need not to be crammed up. These expressions need to be understood first. So if you are able to understand this power flow, you will be able to write all these expressions depending upon or how you understand this power flow. So power flow needs to be understood first, and then these expressions needs to be written, and then on the basis of this you need to attempt few numerical problems. So once you will be dealing with numerical problems, then the concepts will become more clear, and for that you may refer few solved problems first based upon losses and efficiency, and then try some unsolved problems, because if you are not attempting the unsolved problems, then you will not be able to come across how you or how far you have understood the topic correctly. So attempting the unsolved problem is a must part of this particular topic, and you need to attempt this few unsolved problems. So on the Google Classroom, I'll be giving you few solved problems and then few unsolved problems as your assignments. So you are required to attempt first few solved problems, and then you will be solving those unsolved problems which are basically depending upon the topic which I have discussed here. So I hope you will be understanding this topic first, then attempting the few solved problems, and then after attempting the unsolved problems, this topic will be